Welcome. So in this video, we will just summarize what we have been discussing in this module, just to connect dots, and a lot of it would be already some repeated information. Yeah, but just to emphasize some of the main concept and show how you could put these concepts into application. Yeah, so you will, by the end of this video, you should be able to identify the analysis method for and the aquifer test, giving the study purpose and the available resources. So like which aquifer test you're going to use, and oops, as we will learn about them. We learned one aquifer test so far, which is pumping test, but there are others. So which aquifer test you use, and like each of these methods, like with pumping test, there are like these methods. This is the Walton method for leaky aquifers. There's the Neumann method for the unconfined aquifer. So you should be able to also identify like which analysis methods are you going to use. Yeah, and that would depend on like the study purpose and like available resources. Yeah, and your aquifer, of course. Yeah, and then you will like discuss, and you should be able to design and interpret results from the pumping test. So you should be able to do this, even though we didn't cover all aquifer tests and we didn't cover all analysis method, but we will discuss this in this video. Right, so let's get started. So before, let me just tell you some important aspects that we briefly mentioned them before, but let's talk more about them. So one thing, remember, like from C's method, for example, like C's method, I told you C's method is valid. Like if you want to use C's method, it is valid if your well is fully penetrating, and that goes for like your pumping well, and your observation well is fully penetrating. So that is like C's method is valid. But in certain cases, that might not be the case. It might not be like your pumping well might not be fully penetrating, as you see here. So this is a fully penetrating observation well. This is not a fully penetrating observation well. This is not a fully penetrating, like partially penetrating, like a pumping well. Yeah. So you see here like three example. Yeah. So when your partial penetration, when it's partial penetration, the problem of this partial penetration is that now you started to have like not horizontal groundwater flow, but also you start to have like this like vertical gradients. Yeah, so you start to also have like a vertical gradients into your flow. So if you have a partially penetrating observation or pumping well, that should be an issue. Like this effect could be negligible, provided that the length of the well screen is close to the saturated thickness. So here, this is like your saturated thickness, and this is your well screen. So if, as long as you are close to this saturated thickness, where you predominantly have like this horizontal flow here. Yeah. The observation well is fully penetrating. Like your observation well is fully penetrating, so you're getting like it's all like horizontal flow. Yeah. Or the observation well, and your observation well is located sufficiently far away. So R should be, that's how you calculate R, should be larger than, like the distance here should be larger than 1 over B, that's B, and vertical hydraulic conductivity, horizontal hydraulic conductivity versus vertical hydraulic conductivity. So R need to be larger than this. Then in that case, that should be fine. Like even if your well is not fully penetrating, because you still has some like vertical gradient here, vertical. Sorry, horizontal flow here. Yeah, no vertical gradient. So you need to account for this in mind, and that's why when you enter, remember when you use Aquatisolve, it was telling you, asking you this question, like what is the B? Where is your screen length? Is it here? Is it fully penetrating? Is it partially penetrating? It was, where is R? So it was asking you for all this. So if these corrections are needed before conducting your analysis, and like to account for like that your well is not fully penetrating or something like this, then it can be account for this, and software could account for this. So that's like one thing you need to account, like whether like the effect of partially penetrating well, and you need to consider this and account for this. And software like Aquatic Solve will could account for this issue, yeah, and take this into consideration when calculating your estimating your aquifer properties. Okay, another thing also that you need to account for is something called like well loss. And well loss, let's treat it, is the difference between the aquifer head and the water level inside the borehole. So what does this mean? So you see here, this is like my static, like let's say this is my static potentiometric surface is here, yeah? And then once you start pumping, your head will drop to here, yeah? But you see the head in the well is much less than, like you have much more drawdown in your well than in this cone of depression. And this is called like well loss. So it's like this is, you here have an extra energy loss. And this extra energy loss, that could be due like to several factors. Like it could be mainly like due to friction loss. So you have like some friction loss, and this friction loss is occurring here at your well. Like, so you have some friction loss here that's occurring at your well, and this friction loss could be caused by like resistance of flow through the well screen, through the filter pack. So here you have like a well screen, you have like well screen, you have formation pack, you have uh, filter back, I mean, and you have this formation like the surrounding your well, yeah. So this could cause this like well loss here. That's called like well loss, and this well loss, it's also a function of several things. It's a function of also your pumping rate, your well diameter, whether you are fully penetrating or partially penetrating. So all these things would be like factors that will determine your well loss. Yeah. So this also things that need to be like taken into consideration when you conducting your analysis, and that's why like it's, as I told you, like software like Aquatic Solve will be asking for this type of information to make some of these correction as needed. But you need to take this into consideration, and we will talk more about the implication of this later, like when we talk about like how, like when will like this impact of well loss will be, like how you could minimize the impact of this well loss. Yeah, we'll talk about this later. But another thing other than the well loss, yeah, uh, is this borehole storage. So what is borehole storage? Like borehole storage, this is the volume of water that's stored in your well pore. So like here is in your well pore. Here you will find that water is already stored here. This water is not coming from the aquifer. This is just coming from your borehole. Yeah. And this can be pumped out before you draw water from the surrounding aquifer. So you have water that is here, borehole storage, and you pump this water out before you start like withdrawing water from your aquifer. Yeah. So that's also, you need to, when you conduct your pumping test, you need to make sure that this data is not from the data that you're collecting is not based on borehole like storage, but this data is you're actually drawing this from the surrounding aquifer. And usually pumping tests are generally not conducted for a well like after you develop your after you develop your borehole. Like, it's usually conducted after you drill. So you drill, you have a borehole, like you drill your borehole, and before developing your well, you start your pumping test. And in that case, you can minimize this impacts of like borehole storage. But if there is borehole storage, then you need to take this into consideration. Like the borehole storage can be take it into consideration before you get like meaningful data for your drawdown time curve. Yeah, and of course, if you have a well that has a very large diameter or screen for like very long interval, like you have a screen for a very long interval or like a very large diameter, then this borehole storage could be considerable, and it could be like a big amount that you need to consider. Okay. Okay. Now another thing, so that is basically like two considerations that you need to consider when like conducting a pumping test. But I also wanted you to introduce these two concepts like the borehole storage and well loss and partially penetrating well, because there are other methods for estimating like aquifer parameters. So as I told you, like pumping that's one of them, but I will show you like in the rest of this video that there are also other methods that for estimating aquifer transmissivity. One of these method, like one of these aquifer tests or method for estimating like aquifer transmissivity, that could be like specific capacity data. So aquifer tests, like a pumping test, are usually not performed when well is in production, and like when not performed when production well are installed, because they are time consuming and expensive. Like, so when production well are installed, like, and you have your casing and you have your packing, and then the production well is installed and is operationable, you could have like this borehole storage effect, you could have well loss effect, you could have all like these different effects. So usually we don't conduct aquifer tests like a pumping test at this stage. Yeah, and aquifer test like a pumping test is also very time consuming, it's expensive. Yeah, so we don't, so we conducted it before, like at the planning stage, before the production well like is installed. Yeah. uh, but if the production well is installed, what you can do, you can also get, you can do like something, you can collect something called like specific capacity data. So the specific capacity data, this is basically the specific capacity is the yield of the well divided by the drawdown. This is called like specific capacity. So basically like Q, like how much water you're getting out, and then like divided by the drawdown, and this is specific capacity data. Okay, and the specific capacity data, this could be also like specific capacity data could be also used to estimate like aquifer transmissivity, and there is like a large body of existing literature on this. Yeah. So basically, specific capacity show how much water well can produce per unit drawdown, where lower value may indicate, like if you have a lower specific capacity data, like lower than what you initially were getting, or lower than like it's getting like slowing with time, that could be also due to like different factors. That could be also like, it could indicate like clogging, it could indicate like poor aquifer connection, or it could indicate like that you have like high head loss. So clogging, that could occur from different reasons. Like it could occur like there are fine sediments or biofouling, or like some chemical precipitants that are blocking your well screen. and the surrounding formation. So, for example, like calcium could be precipitating, and that could plug the screen, yeah, or the surrounding formation, like affect your effective porosity and things like this, and that could restrict water flow, yeah. So, and that's one thing like what you can learn also from specific capacity, like other than like you can estimate like transmissivity, you can see like you can learn about these things like poor aquifer connection, like poor aquifer connections, that's like due would be like due to the inadequate well design, like you have a partially penetrating well, or like your screen is short or poorly developed, uh, or like there are some drilling damage that limits the well ability to access like the full aquifer, so that could be like a poor aquifer connection, yeah. Other thing like for like getting like low, like your specific capacity is knowing is like head loss, yeah, high head loss. So high head loss, that would be like excessive drawdown when could make like turbulent flow, and this like improper screen design, or like you're pumping too fast, that could cause turbulent flow, and that could cause energy loss beyond the aquifer natural resistance, yeah. So that's also things that you could learn from specific capacity. And specific capacity, that is basically like you measure Q, you measure drawdown, and then you can monitor like your specific capacity over time. And if you want to learn more about like specific capacity and how to specific analyze the specific capacity data, you can check your textbooks, yeah, any of your textbooks, whether the free one or the fetter one, yeah. So that's like you can learn more about this specific capacity data. Okay, now, so we learned about several things. We learned about specific capacity, yeah. We learned about partially penetrating well. We learned about well loss and borehole storage. So now let's see this like a single aquifer test, like a pumping test. So in the pumping test, remember, like pumping test, like pumping and drawdown is measured in the same well, yeah. So limited by well loss and well bore storage. So this could affect like your pumping test if you are using a single well aquifer test. Remember like the video we showed, like they were using a single aquifer test, and I told you usually like a better way is like you have like a pumping well and the mono and an observation well. So you have a pumping well, that's what we did with our previous exercises, was a pumping well, and then there was an observation well. So if you have a pumping well, you're pumping from somewhere and you're observing somewhere, that will eliminate this problem of like well loss and well borehole storage. Why? Because you are not measuring like drawdown in your pumping well, you are measuring drawdown in your observation well. So you don't get like these two issues, like well loss and well bore storage. And that's why it is usually like a good idea to conduct your pumping test uh, using like two well, at least two well, a pumping well and an observation one. And you can have multiple observation well, as we also discussed. Like you could be measuring like drawdown in multiple observation wells. So you have observation well 2, like observation well 3, observation well 5, and then you measure drawdown. And remember, you can do like a distance drawdown curve, or you can do time drawdown curve. Like you can use st or s, like distance, yeah, like distance, yeah, length or whatever. St like this, sr, yeah, let's call it sr, yeah. So you can also, and we briefly looked, like we mainly looked at this one, but I also briefly mentioned this one, yeah. If you have multiple observation well, so to get rid to avoid like this problem of well loss and well pore storage, we generally don't do like a single aquifer test, yeah. But if you did it like and you use a software like Aquatisolve that can account for well loss and well pore storage, like you adjusted this through your software, you can provide like an estimate, a rough estimate of transmissivity. Your estimate for storativity will not be reliable because of like the well pore storage, so that could also have like an impact on it. Uh, But the focus is like if you did like a single well aquifer test, or like if you're doing aquifer test like using a single well, you can estimate like a specific capacity and you could estimate efficiency. So we talked about a specific capacity. Specific capacity show how much water will be can be produced per unit drawdown, where lower value may indicate like clogging, poor aquifer connection, or higher head, as this value gets lowered over time. But also, like if you have a single well, you can do like well efficiency. So well efficiency is just like theoretical drawdown and actual drawdown. So theoretical drawdowns, that's the drawdowns that you did, for example, with uh, that the theoretical drawdown and then the actual drawdown that you are getting. Yeah, and this, if you see like the deviation between like the theoretical drawdown from like your C curve or whatever and like the actual drawdown, that could tell you something about like the well efficiency. So well efficiency capture whether poor performance is due to well construction like design, like screen puncture, or the aquifer limited ability to transmit water. Yeah, so that's like well efficiency. So basically like, because sometimes your poor performance is not due to the aquifer ability to transmit water, but it's just poor well construction or design. Yeah, and that you can get this from like a single aquifer test. Single aquifer test might provide information about this. Again, if you want to learn about this, you can check like any of your textbook, and then you will find like start like you will find information that will get you started to learn more about this. And there is like a big literature on these topics which you can also check. Yeah. Uh, Another thing also, like just be to conclude the pumping test, is that like when you conduct a pumping test, what are you observing? You are observing like a drawdown with time. Yeah. So you're pumping the water out, and as you are pumping the water out, you'll draw down. So this is the time. Yeah. Your drawdown will like increase with time. But once you stop pumping, what will happen? You will start to recover. Yeah. So your water level will start to recover. Uh, why don't you also monitor like the recovery? So not just the pumping time, but the recovery data, and this data could be analyzed also. Yeah, so that's like you will have two set of data, like you have pumping data and recovery data, like drawdown data, and this is called like residual drawdown data. So you have a drawdown data and residual drawdown data, and again there is also methods similar to C's method, and these methods that you could or whatever methods that you could use to do the recovery data. So that like you will have like two sets of data. So there is like a race recovery. There is a method for calculating aquifer characteristic from this recovery data, just as there are methods for calculating aquifer characteristic from pumping data. There is also from recovering data. And usually, again, for like recovery data, you usually do this from observation well, as pumping well, like recovery data could be like less useful. Okay, so this is pumping test, yeah. So that's just like a conclude discussion about pumping. But other than pumping tests, there is also other tests like that are cheaper than pumping tests, and this is called like slug test. So this is among other like aquifer tests for estimating aquifer parameters. Like so, you conduct like a slug test. Uh, so a slug test is simple, like it's like a known volume of water is quickly taken or added to the well, and then so you add this to the well or quickly remove it from the well, and then the rate at which the water level fall or rise is measured. That's it. Like so, you add or you remove water to your well, and then you measure the rate of water falling or rising. This is an expensive alternative to pumping well, uh, but it estimates the aquifer parameter at much smaller areas than a pumping test. Yeah, so but it's less inexpensive, yeah, compared to a pumping test, but it will measure your parameters at like smaller areas than pumping test. Yeah. Uh, Also, in other than that, like other than being like this is like a cheap version of a pumping test. It also has some merits on its own. Yeah. So in some field investigation, for example, you might need to know the hydraulic conductivity of low permeable material, like your aquitart. Yeah, like this low permeable material. And if this is the case, pumping test might not be feasible because conducting pumping from this low permeability region, you can like when you have this like low hydraulic conductivity, uh, this would be like you're too low to conduct a pumping test, like because the water will not be flowing. So that would be too low to conduct a pumping test. In that case, a slug test would be useful. Other advantage of the slug test, also other than the pumping test, if you are in a contaminated site. So if you are in a contaminated site, you don't want to pump this water out because if you pump this water out, and that could be like not necessarily a contaminated site, like if like a like landfill or like some uh, whatever, like aqua or like a contaminated site or something where the water is groundwater is contaminated. You don't want to conduct a pumping test and pump like this contaminated water out because if you pump this contaminated water out, you have to treat it before you dispose it. Yeah. So in that case, also a pumping test might not be feasible. And here, like slug test might be more feasible to conduct. Yeah. So you can Okay, so measuring hydraulic conductivity across the scale. So we've seen so far several like ways of measuring like hydraulic conductivity. Like we've seen like a permeameter, like so here is an example of we talked about this Satur infiltrometer or like a falling head permeameter or constant head permeameter, which you can do either in the lab or in the field, like the falling head permeameter. You can also do this in the field, not necessarily in the lab or like this like this infiltrometer. Yeah, so this will give you like at small scale, like at a soil sample like scale. Yeah, slug test would be slightly like larger scale, like meters of scale, and the pumping test will give you like tens or hundreds of like meters of scale, like depending how big your pumping test you're conducting is. And can there be like kilometer scale? Yes, there could be even kilometer scale, not to measure hydraulic conductivity, but to characterize hydraulic conductivity. Like for example, air-prone geophysics. So there are air-prone geophysics method, like you have like a helicopter flying out and measuring taking some images of the subsurface, and from this images of the subsurface you can also characterize the hydraulic conductivity field. It will not give you a measure of like the hydraulic conductivity value, but you can characterize like different zones like permeable, impermeable, things like that. Yeah. And geophysical imaging in general, which we will talk about this in next module. But for the aquifer test, that would be like a centimeter scale to tens of meter scale. Like that would be the pumping test. That would be the most expensive. That would be the cheapest one to conduct. Yeah. Uh, this is a slug test, so like in the links, like also check like the notes of this video. I put some links to some useful resources. So this, for example, like what you see in this image here, this is slug test analysis of selected well in New York, yeah, and then this is a USGS report. It talks about like the test, like the slug test, and like design and analysis. So that would be an excellent source to learn about slug test other than your textbook. Okay, so let's just summarize and sum up what we have been doing. Like uh, aquifer test, like what to consider, like why do we, what to consider. So what to consider, like when you conduct an aquifer test, like somebody tell you, okay, like your supervisor told you go do an aquifer test, like what do you need to consider? The first thing you need to consider is you ask him why. Why do you want to do an aquifer test? Why do you want to do a pumping test? So when you do anything, whether like an aquifer test, whether in groundwater hydrology, whether in any water resources problem, or in general, yeah, you need to define the purpose. So that's the most important thing, like the purpose of the pumping test, because the purpose of the test will di- dictate, or based on the purpose, you will decide like which aquifer test you will need and which method are you going to use for analysis. Or even if you need an aquifer test at all, because maybe for this purpose we can answer this question without doing any aquifer test, or this data already exists. Yeah, or giving like the data we have, we can answer this question. So that's the most important thing, like what to consider. The most important thing to consider is the purpose, like that must be established first. uh, and then of course you need to adequate design and execution. So like the adequate design of your test will involve like considerable planning and attention to detail. So that is also another thing that you need to see, like your pump, you need to get like all these different tools, and when you go to the field, like there are field, like going to the field, it is time consuming, yeah, and it requires careful planning. So and you need to get, so like usually like when we do field work, we have a van full of tools and instrument, yeah, that will help us in the field. So that requires like adequate design and execution. But more than this tools and instrument is that you need to have a good understanding of what you're doing, like a good understanding of the well hydraulics. So before you go to the field, before you even start like designing and execution, make sure that you have a good understanding of what you are doing. And that's why I put like these sources for you, yeah? Like if you want to conduct a pumping test, like this video will not be sufficient, yeah. So like if you want to conduct a pumping test, you need like, for example, like chapter 5, like this is chapter 5 of your textbook, like the fitter one, but here you have like a full book about like aquifer tests. So this is even an introduction to hydraulic testing, yeah. So you need to get like a book like this and study it very carefully. And then this book will guide you to specialized sources. So this book will guide you to specialized sources. And then you need to, whatever, like if you're doing a slug test, if you're doing a pumping test, if you are doing uh, whichever test, like you need to, before you go to the field, you need to be prepared and you need to understand the theory behind this. This will save you a lot of trial and error in the field, and this will also save you if you did something wrong, you wouldn't need to go and repeat like this analysis again, yeah. That's the last thing you want, yeah, that you miss something or you misunderstood something and then you have to repeat this analysis again. Okay. uh, And then again, like you can, like if you just drilled a new well and you kept pumping it, you will, that will tell you about this yield of the new well. But if you carefully conducting a pumping test where you are measuring like drawdown with time, or draw down with distance, if you have multiple observation well, then you will not only know about like the yield of this new well, but you can also know about like the aquifer transmissivity or hydraulic conductivity, yeah. And you can also know about like the general type of the aquifer. Okay, so what can be detected? So we already talked about this, like what can be detected, whether this is an unconfined, like semi-confined or a confined aquifer. And we looked at this what can also be detected is that like if there is like a recharge or if there is like a barrier boundary, and we talked about this. So like again, this is just like a review of what we did. So here, remember we talked about this. So this would be the ideal case, that would be the unconfined case, that would be the leaky case, and that would be the impermeable and constant head. So all this could be detected from a carefully designed pumping test. You can learn all this, yeah? That's what can be detected, yeah? So we talked about this already, so this is just like a summary. Uh, let's go back. So that's what can be detected. What can be quantified? We can quantify a lot. We can quantify the storage coefficient. We can quantify the hydraulic conductivity value. We can also quantify the vertical hydraulic conductivity. If we are using the Walton method, like if this is a like if this is a leaky aquifer, and we can confine the anisotropy and specific yield and specific storage if this is an unconfined aquifer and we are using the Neumann method. So a lot can be quantified. Like remember, like these, let me just remind you. I will just select, let's see the, let me go back to the, here. Remember we did this. So that's like the leaky aquifers, the Walton method. So what can we quantify? We can quantify like the S. We can, oops. We can quantify the S, we can quantify the T, and we can quantify the K of the hydraulic conductivity of this leaking area. So that's, for example, what can be quantified. And for the Neumann method, remember like this is the Neumann method. Uh, what can be quantified is a lot actually. You can quantify like the T. Oops. You can quantify like the T. You can quantify the S. You can quantify the specific yield. You can quantify the KZ and the KR. So you, from these two, you get like your anisotropy. Yeah. So that's, so you can quantify a lot from these tests. Yeah. So let's go back here to our slide. Okay. So okay, now here is like a poorly designed, that like you can do this if you, if your aquifer, like your pumping test or aquifer test is like well designed, yeah. But a poorly designed aquifer test that might can produce like inaccurate or unreliable data, yeah. So you need to have like carefully designed, like you need to have appropriate pumping rate, appropriate duration, and observation well configuration. So if the pumping rate, for example, like is too high, the drawdown could be like too rapid and it may cause even the well to dry, make it impossible to get like accurate data, yeah. If the pumping rate is too low, on the other hand, then what will happen? The drawdown might be insufficient or inaccurate, very small drawdown, and you're not really getting any drawdown or anything meaningful. The duration of the pumping test. If like it's too short, the water level may not have time to stabilize, and then you cannot take accurate measure. So like you see, for all of the pumping tests we conducted, we were pumping for at least a couple of hours, like 2 or 3 hours. Yeah. I mean, if it's also too long, that might be, you might already reach like stabilization phase and like you'll be just like not getting any new information. Yeah. In like also like yeah, in appropriate like observation well configuration. So that's like the placement of the observation well relative to the pumping well is critical. And we talked about like the, when you have a partially penetrating well, for example, what distance you need to keep between like your observation well and your pumping well. So that's something you need to consider. Because if your observation well is also close to the pumping well, that might be affected by well pore storage or or might not accurately measure the hydraulic property of the aquifer if you're too close. Yeah. If the observation well is too far, you might not capture the full extent of the drawdown of the aquifer, or the drawdown might be very small to get like any meaningful analysis. So that is also something that you need to consider. Well configuration could also be like the inaccurate like well screening or casing placement. So if the placement of the well screen or the casing, that's important, yeah, because if the casing is placed in portion of the aquifer, let's say your casing, you are placing the casing in the portion of the aquifer that's clay, that you will not be pumping, you'll not be able to conduct a pumping test. You'll not be able even where you have very low hydraulic conductivity. So you need to place your casing where it's most representative for your aquifer, and that would require knowing about the geology of the subsurface. So that's one thing you also need to do before pumping test, is that you learn about the geology of the subsurface. So you get like existing report like USGS report or report from the water management districts or this information, and learn about your subsurface before you conduct your pumping test. So yeah, in correct well screening like placement sands or clay. Yeah. Now another thing like poorly like others than like so you can poorly design the pumping test, and that would reduce inaccurate or unreliable data, and then you have to repeat it. But you can conduct an accurate pumping test. So pumping test is okay, but you misinterpret the data, and if you misinterpret the data, that will result in incorrect conclusion or ineffective groundwater management strategy. Yeah. So proper data interpolation, like knowledge of the well hydraulic, and again, how you could properly interpret the data, you should have a good knowledge of well hydraulic, where you can, for example, identify the source of the water entering the well. You can identify if there is impermeable boundary, so you'll know the effect of like a of and you think that this is obvious because you learned it, but for someone who didn't learn these things, he's pumping near a stream, and he will get a data that doesn't make sense or doesn't align with this theoretical curve, and he say, "Oh, why my results are so screwed up?" Well, it's not so screwed up. It's just like you need to understand that if you are uh, pumping near like a stream, you need to account for this, yeah, and you need to understand the methods that account for this as we studied them here in this lesson. So without understanding, you may misinterpret or misunderstood the data or think that there's something wrong with your pumping test. Well, your pumping test is fine, but you just don't understand like the well hydraulic effect of boundaries and or like a leaky aquifer or things like that. Yeah. So failure to account for well pore storage. So we talked about like the well pore storage and the failure to account for this. Yeah. So if the effect of well pore storage are not accounted for, that may result in misinterpret misinterpretation or indicating like that the hydraulic conductivity could be that you will estimate would be very different than the hydraulic conductivity of the actual formation. So you need to account for, yeah, like for this well poor well storage, and one way to do this is that you have like your pumping well and an observation well, and the observation well would be like at a distance that's far away, not too far and not too close to your pumping wells. That's one way to account for this. Now, another thing is failure to consider the heterogeneity of the aquifer. So the aquifer is heterogeneous, as we have seen before, yeah, as we have seen several times. And if this heterogeneity is not taken into account, that could lead to an inaccurate estimate of the hydraulic conductivity. So, for example, like if you are conducting your pumping test in a more permeable area than the surroundings, that may result in overestimating your hydraulic conductivity for the entire aquifer. And that's why we generally conduct several pumping tests at different locations, as we will see like in your modeling case study, you will be giving like, so the case study would look something, oops, like this, and then we conducted a pumping test here, 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 and then like it's like more of like an art and science to see like, okay, so this pump, like based on like this pumping test data and based on some geophysics data, you will see, okay, maybe this pumping test is good for this region, this pumping test value is good for this region, this pumping test value is good for this region. And then and you will do this. So that's part, like we will do this in the next module. Yeah, is like you will see the failure to how you could consider heterogeneity. So that's what we will be doing next. Failure to consider the effect of boundary condition. Again, we talked about this. Like if you have like a nearby stream, you will get your water will be recharged from this stream, and then once your water get recharged from this stream, that could result, if you didn't take this into account and in your consideration, that could result in overestimating like your hydraulic conductivity. Yeah, you will get a higher hydraulic conductivity. Okay, let's say now you did everything correct. Yeah, you designed your well correctly, you interpret your data correctly. That's not it actually. So let's say I designed my pumping test correctly. I did all these things correctly. So I have a good understanding of well hydraulics. I accounted for well storage. I consider heterogeneity. I consider the effect of boundary condition, and I did my analysis correctly. That's not actually the end of the story, because sometimes you could have incomplete or inaccurate information, and that could lead to unsustainable use or over exploitation of your groundwater resources. So sustainable groundwater management, that's the central topic in water resources management. Yeah. Uh, so so like this, when you do this like aquifer test, like a pumping test or a slug test or like any test, this will help you to determine the location of the new well that you want to do, whether this like a pumping well, this is a monitoring well. So this will help you to to decide where to put like your well, and where you want to invest, and where is the best location for pumping, or where is the best location for monitoring. And without like this understanding, like this broad understanding, like uh, groundwater management decision may be based on incomplete or inaccurate information, and this would lead to unsustainable use or over exploitation of your groundwater resources. And that's why we take this information, like, so I will estimate specific yield, I will estimate hydraulic conductivity, I will take this information, put it in a model, and like this model will guide my decision, and will guide my groundwater uh, decision. So another thing is like the ignoring the effect of pumping on nearby wells or surface water resources. So here in Florida, if you want to have a new pumping well, what they will do, like in Southwest Florida Water Management District, like you will want to have a new pumping well. What they will do is that they will run this new pumping well in their existing model. So they have a model. So they'll have a model for the region. They will run this well on this existing well with the amount of water that you need, and then they will see how will this well that you are proposing will affect like nearby well, and will affect like surface water resources, like the stream, nearby stream. Because remember, if you are pumping like near like a stream, you would be capturing no water from that stream. You will not be drawing water from storage, but you will be capturing water from this stream. So your water will be coming from this stream, and your water level you'll draw down, as we've seen, will remain the same. And this water will be captured from stream. So here, for example, in Florida, that's what the water management, that's the permitting process, and that's what the water management districts will do, is that they will ask you to show the impact of this well on the nearby well and surface water resources, and like dependent and the groundwater dependent ecosystem as well. Yeah. And then without understanding like well hydraulics and how you groundwater capture, for example, how you are not capturing this from storage, but you are capturing this from nearby stream, then these you will lead again to unsustainable use and unsustainable decisions. So So that's also something you need to take into account. Yeah. And then, of course, pumping water from a well that is faster than it could be replenished. So there is a whole topic about this. It's called like groundwater sustainability. Not all well are renewable at a human time scale. Some of these aquifers, they are renewable at a geological time scales, and in that case again you can also need to account for this, and then you need to like strategically like use this available water and use it sustainably so that you will not like you fulfill the need of the current generation without like impacting the next generation. Yeah. And then you can also overestimate your available groundwater resources, and that could be due to like as we talked about, like you are not taking into account the impact of boundaries. You are not taking into account like like other of these errors that you can do in like your well design or interpreting your data. Yeah. So without like overestimating like the available groundwater resources uh, will including like recharge and how this is getting recharged, that could also impact like your long-term lose of this resources. And I showed you like if you look at the if you want to, or here I have it here. Yeah. So you can look read like if you want to read like these things in detail, like I cannot cover this in detail like in such a short amount of time, but if you want to read this in detail, please check like this paper here. So this has a lot of information, and check this video here. So this video is like an updated version of this paper, and it shows like example like from Hawaii uh, where I used to work before, and it shows example, for example, like of how you can estimate the available groundwater resources. And if you looked into the future impact of climate change, how could this lead to unsustainable water management in the future, like the salinization of your aquifer or things like that. Yeah. So I think that's all for this video. Please check this video. It's a very like it will like after like taking like looking at a lesson like this video will make much more sense now, like groundwater sustainability. And you will see like we are talking like in this video I talk about like all these topics but in details with more information. Yeah, not just quickly going over it. I think that's all for this module. In the next module, what we will be doing is that we will look into like start to bring whatever we have learned, we will put it all into a case study, and we will do some real life project type of project or characterization of our subsurface and then model